Let us now endeavor to get some idea of the significance of the principle by the consideration of a few simple examples that cannot be dealt with by the ordinary method of the lever, the inclined plane, and the like. The differential pulley of Weston, figure 45, consists of two coaxial rigidly connected cylinders of slightly different radii, R1 and R2 less than R1. A cord or chain is passed round the cylinders in the manner indicated in the figure. If we pull in the direction of the arrow with the force P and rotation takes place through the angle phi, the weight Q attached below will be raised. In the case of equilibrium, there will exist between the two virtual moments involved the equation Q times the difference of R1 and R2 over 2 multiplied by phi equals P times R1 times phi. Or in other words, P equals Q times the difference R1 minus R2 over 2R1. A wheel and axle of weight Q, figure 46, which on the unrolling of a cord to which the weight P is attached, rolls itself up on a second cord wound round the axle and rises, gives for the virtual moments in the case of equilibrium the equation P times the difference R minus R multiplied by phi equals Q times R times phi, or P equals QR over R minus R. In the particular case R minus R equals 0, we must also put for equilibrium Q equals 0. Or for finite values of R, Q equals 0. In reality, the string behaves in this case like a loop in which the weight Q is placed. The latter can, if it be different from 0, continue to roll itself downwards on the string without moving the weight P. If, however, when R equals R, we also put Q equal to 0, the result will be P equals 0, an indeterminate value. As a matter of fact, every weight P holds the apparatus in equilibrium, since when R equals R, none can possibly descend. A double cylinder, figure 47, of the radii R lies with friction on a horizontal surface, and a force Q is brought to bear on the string attached to it. Calling the resistance due to friction P, equilibrium exists when P equals the fraction R minus R over R times Q. If P is greater than R minus R over R times Q, the cylinder will roll itself up on the string and be fastened. If from these rods we suspend two equal weights P, equilibrium will subsist independently of the position of the points of suspension, because on displacement, the descent of the one weight is always equal to the ascent of the other. Roberval's balance, figure 48, consists of a parallelogram with equal arms at right angles, two opposite sides of which, and the vertical bar above, are capable of rotation about fixed axes. If the two equal pans are fastened to the upper horizontal bar and loaded equally, the system remains in equilibrium whatever be the position of the pans. If from these rods we suspend two equal weights P, equilibrium will subsist independently of the position of the points of suspension, because on displacement, the descent of the one weight is always equal to the ascent of the other. At three fixed points A, B, C, figure 49, let pulleys be placed, over which three strings are passed loaded with equal weights and knotted at O. In what position of the strings will equilibrium exist? We will call the lengths of the three strings AO equals S1, BO equals S2, CO equals S3. To obtain the equation of equilibrium, let's displace the point O in the directions S2 and S3 the infinitely small distances delta S2 and delta S3, and note that by so doing, every direction of displacement in the plane ABC, figure 50, can be produced. The sum of the virtual moments is P delta S1 minus P delta S1 cos alpha plus P delta S2 cos of alpha plus beta plus P delta S3 minus P delta S3 cos beta plus P delta S3 cos of alpha plus beta equals 0. Or, grouping terms by the chosen independent displacements, square bracket 1 minus cos alpha plus cos of alpha plus beta, close bracket, times delta S2, plus square bracket 1 minus cos beta plus cos of alpha plus beta close bracket times delta S3 equals 0. But since each of the displacements delta S2, delta S3 is arbitrary, and each independent of the other and may by themselves be taken equal to 0, it follows that 1 minus cos alpha plus cos of alpha plus beta equals 0, and 1 minus cos beta plus cos of alpha plus beta equals 0. Therefore, cos alpha equals cos beta, and each of the two equations may be replaced by 1 minus cos alpha plus cos 2 alpha equals 0, or cos alpha equals 1/2, wherefore alpha plus beta equals 120 degrees. Accordingly, in the case of equilibrium, each of the strings makes with the others angles of 120 degrees, which is moreover directly obvious, since three equal forces can be in equilibrium only when such an arrangement exists. This once known, we may find the position of the point O with respect to ABC in a number of different ways. We may proceed, for instance, as follows. We construct on AB, BC, CA severally as sides equilateral triangles. If we describe circles about these triangles, their common point of intersection will be the point O sought, a result which easily follows from the well-known relation of the angles at the center and circumference of circles. A bar OA, figure 51, is revolvable about O in the plane of the paper and makes with a fixed straight line, OX, the variable angle alpha. At A, there is applied a force P, which makes with OX the angle gamma, and at B, on a ring displaceable along the length of the bar, a force Q, making with OX the angle beta. We impart to the bar an infinitely small rotation, in consequence of which B and A move forward the distances delta S and delta S1 at right angles to OA, and we also displace the ring the distance delta R along the bar. The variable distance OB we will call R, and we will let OA equal A. For the case of equilibrium, we have then QR cos of beta minus alpha plus Q delta S sine of beta minus alpha plus P delta S1 sine of alpha minus gamma equals 0. As the displacement delta R has no effect whatever on the other displacements, the virtual moment therein involved must by itself equal 0. And since delta R may be of any magnitude we please, the coefficient of this virtual moment must also be 0. We have, therefore, Q cos of beta minus alpha equals 0, or when Q is different from 0, beta minus alpha equals 90 degrees. Further, in view of the fact that delta S1 equals A over R times delta S, we also have RQ sine of beta minus alpha plus a P sin of alpha minus gamma equals 0. Or, since sine of beta minus alpha equals 1, RQ plus a P sin of alpha minus gamma equals 0, wherewith the relation of the two forces is obtained. An advantage, not to be overlooked, which every general principle, and therefore also the principle of virtual displacements, furnishes, consists in the fact that it saves us to a great extent the necessity of considering every new particular case presented. In the possession of this principle, we need not, for example, trouble ourselves about the details of a machine. If a new machine, say, were so enclosed in a box, figure 52, that only two levers, projected as points of application for the force P and the weight P prime, and we should find the simultaneous displacements of these levers to be H and H prime, we should know immediately that in the case of equilibrium, pH equals P prime, H prime, whatever the construction of the machine might be. Every principle of this character possesses therefore a distinct economical value. We return to the general expression of the principle of virtual displacements in order to add a few further remarks. If at the points A, B, C, and so on, the forces P, P prime, P double prime, and so forth act, and P, P prime, P double prime are the projections of infinitely small mutually compatible displacements, we shall have for the case of equilibrium PP plus P prime plus P double prime, and so on equals 0. If we replace the forces by strings which pass over pulleys in the directions of the forces, and attach thereto the appropriate weights, this expression simply asserts that the center of gravity of the system of weights as a whole cannot descend. If, however, in certain displacements it were possible for the center of gravity to rise, the system would still be in equilibrium, as the heavy bodies would not, of themselves, enter on any such motion. In this case, the sum above given would be negative, or less than 0. The general expression of the condition of equilibrium is, therefore, PP plus P prime plus P double prime, and so on, is less than or equal to 0. When for every virtual displacement there exists another equal and opposite to it, as is the case, for example, in the simple machines, we may restrict ourselves to the upper sign, that is, to the equation. For if it were possible for the center of gravity to ascend in certain displacements, it would also have to be possible, in consequence of the assumed reversibility of all the virtual displacements, for it to descend. Consequently, in the present case, a possible rise of the center of gravity is incompatible with equilibrium. The question assumes a different aspect, however, when the displacements are not all reversible. Two bodies connected together by strings can approach each other but cannot recede from each other beyond the length of the strings. A body is able to slide or roll on the surface of another body. It can move away from the surface of the second body, but it cannot penetrate it. In these cases, therefore, there are displacements that cannot be reversed. Consequently, for certain displacements, a rise of the center of gravity may take place, while the contrary displacements, to which the descent of the center of gravity corresponds, are impossible. We must therefore hold fast to the more general condition of equilibrium and say the sum of the virtual moments is equal to or less than zero. Lagrange, in his Analytical Mechanics, attempted a deduction of the principle of virtual displacements, which we will now consider. At the points A, B, C, and so on, figure 54, the forces P, P prime, P double prime act. We imagine rings placed at the points in question, and other rings A prime, B prime, C prime fastened to pulleys lying in the directions of the forces. We seek some common measure Q over 2 of the forces P, P prime, P double prime that enables us to put 2n times Q over 2 equals P, 2n prime times Q over 2 equals P prime, 2n double prime times Q over 2 equals P double prime, where n, n prime, n double prime, and so on are whole numbers. Further, we make fast to the ring A prime A string, carry the string back and forth n times between A prime and A, then through B prime, n prime times back and forth between B prime and B, then through C prime, n double prime times back and forth between C prime and C, and finally let it drop at C prime, attaching to it there the weight Q over 2. As the string has now in all its parts the tension Q over 2, we replace by these ideal pulleys all the forces present in the system by the single force Q over 2. If then the virtual, that is, possible displacements in any given configuration of the system are such that these displacements occurring, a descent of the weight Q over 2 can take place. The weight will actually descend and produce those displacements, and equilibrium therefore will not obtain. But on the other hand, no motion will ensue if the displacements leave the weight Q over 2 in its original position, or raise it. The expression of this condition, reckoning the projections of the virtual displacements in the directions of the forces positive, and having regard for the number of the turns of the string in each single pulley, is 2np plus 2n prime p prime plus 2n double prime p double prime, and so on, is less than or equal to 0. Equivalent to this condition, however, is the expression 2n times q over 2p plus 2n prime times q over 2p prime plus 2n double prime times q over 2p double prime, and so on, less than or equal to 0. Or finally, pp plus p prime plus p double prime, and so on, less than or equal to 0. The deduction of Lagrange, if stripped of the rather odd fiction of the pulleys, really possesses convincing features, due to the fact that the action of a single weight is much more immediate to our experience and is more easily followed than the action of several weights. Yet, it is not proved by Lagrangian deduction that work is the factor determinative of the disturbance of equilibrium, but is, by the employment of the pulleys, rather assumed by it. As a matter of fact, every pulley involves the fact enunciated and recognized by the principle of virtual displacements. The replacement of all the forces by a single weight that does the same work presupposes a knowledge of the import of work and can be proceeded with on this assumption alone. The fact that some certain cases are more familiar to us and more immediate to our experience has as a necessary result that we accept them without analysis and make them the foundation of our deductions, without clearly instructing ourselves as to their real character. It often happens in the course of the development of science that a new principle perceived by some inquirer in connection with a fact is not immediately recognized and rendered familiar in its entire generality. Then, every expedient calculated to promote these ends is, as is proper and natural, called into service. All manner of facts in which the principle, although contained in them, has not yet been recognized by inquirers, but which from other points of view are more familiar, are called in to furnish a support for the new conception. It does not, however, beseem mature science to allow itself to be deceived by procedures of this sort. If, throughout all facts, we clearly see and discern a principle which, though not admitting of proof, can yet be known to prevail, we have advanced much farther in the consistent conception of nature than if we suffered ourselves to be overawed by a specious demonstration. If we have reached this point of view, we shall, it is true, regard the Lagrangian deduction with quite different eyes, Yet it will engage, nevertheless, our attention and interest and excite our satisfaction from the fact that it makes palpable the similarity of the simple and complicated cases. Maupertuis discovered an interesting proposition relating to equilibrium, which he communicated to the Paris Academy in 1740 under the name of the Loi de Repos. This principle was more fully discussed by Euler in 1751 in the Proceedings of the Berlin Academy. If we cause infinitely small displacements in any system, we produce a sum of virtual moments, pp plus p prime plus p double prime, and so on, which only reduces to zero in the case of equilibrium. This sum is the work corresponding to the displacements, or since for infinitely small displacements, it is itself infinitely small, the corresponding element of work. If the displacements are continuously increased until a finite displacement has been reached, the elements of work will, by summation, give the actual amount of work. So if we start from any given initial configuration of the system and pass to any given final configuration, a certain amount of work will have to be done. Now, Maupertuis observed that the work done when a final configuration is reached, which is a configuration of equilibrium, is generally a maximum or a minimum. That is, if we carry the system through the configuration of equilibrium, the work done is previously and subsequently less or previously and subsequently greater than at the configuration of equilibrium itself. For the configuration of equilibrium, pp plus p prime plus p double prime, and so on equals zero. That is, the element of the work, or the differential, more correctly, the variation of the work, is equal to zero. If the differential of a function can be put equal to zero, the function has generally a maximum or minimum value. We can produce a very clear representation to the eye of the import of Maupertuis' principle. We imagine the forces of a system replaced by Lagrange's pulleys with the weight q over 2. We suppose that each point of the system is restricted to movement on a certain curve, and that the motion is such that when one point occupies a definite position on its curve, all the other points assume uniquely determined positions on their respective curves. The simple machines are, as a rule, systems of this kind. Now, while imparting displacements to the system, we may carry a vertical sheet of white paper horizontally over the weight q over 2, while this is ascending and descending on a vertical line, so that a pencil which it carries shall describe on the paper the required points A, C, D of the curves. We see adjacent positions in the system of points at which the weight q over 2 will stand higher or lower than in the configuration given. The weight will then, if the system be left to itself, pass into this lower position and displace the system with it. Accordingly, under conditions of this kind, equilibrium does not subsist. If the pencil stands at E, then there exist only adjacent configurations for which the weight q over 2 stands higher. But of itself, the system will not pass into the last named configurations. On the contrary, every displacement in such a direction will, by virtue of the tendency of the weight to move downwards, be reversed. Stable equilibrium, therefore, is the condition that corresponds to the lowest position of the weight, or to a maximum of work done in the system. If the pencil stands at B, we see that every appreciable displacement brings the weight q over 2 lower, and that the weight therefore will continue the displacement begun. But assuming infinitely small displacements, the pencil moves in the horizontal tangent at B, in which event the weight cannot descend. Therefore, unstable equilibrium is the state that corresponds to the highest position of the weight q over 2, or to a minimum of work done in the system. It will be noted, however, that conversely, every case of equilibrium is not the correspondent of a maximum or a minimum of work performed. If the pencil is at F, at a point of horizontal contrary flexure, the weight in the case of infinitely small displacements neither rises nor falls. Equilibrium exists, although the work done is neither a maximum nor a minimum. The equilibrium of this case is the so-called mixed equilibrium. For some disturbances it is stable, for others unstable. Nothing prevents us from regarding mixed equilibrium as belonging to the unstable class. When the pencil stands at G, where the curve runs along horizontally a finite distance, equilibrium likewise exists. Any small displacement in the configuration in question is neither continued nor reversed. This kind of equilibrium, to which likewise neither a maximum nor a minimum corresponds, is termed neutral or indifferent. If the curve described by Q over 2 has a cusp pointing upwards, this indicates a minimum of work done but no equilibrium, not even unstable equilibrium. To a cusp pointing downwards, a maximum and stable equilibrium correspond. In the last named case of equilibrium, the sum of the virtual moments is not equal to 0, but is negative. In the reasoning just presented, we have assumed that the motion of a point of a system on one curve determines the motion of all the other points of the system on their respective curves. The movability of the system becomes multiplex, however, when each point is displaceable on a surface in a manner such that the position of one point on its surface determines uniquely the position of all the other points on their surfaces. In this case, we are not permitted to consider the curve described by Q over 2, but are obliged to picture to ourselves a surface described by Q over 2. If, to go a step further, each point is movable throughout a space, we can no longer represent to ourselves in a purely geometrical manner the circumstances of the motion by means of the locus of Q over 2. In a correspondingly higher degree is this the case when the position of one of the points of the system does not determine conjointly all the other positions, but the character of the system's motion is more multiplex still. In all these cases, however, the curve described by Q over 2, figure 55, can serve us as a symbol of the phenomena to be considered. In these cases also we rediscover the Maupertuisian propositions. We have also supposed, in our considerations up to this point, that constant forces, forces independent of the position of the points of the system, are the forces that act in the system. If we assume that the forces do depend on the position of the points of the system but not on the time, we are no longer able to conduct our operations with simple pulleys, but must devise apparatus, the force active in which, still exerted by Q over 2, varies with the displacement. The ideas we have reached, however, still obtain. The depth of the descent of the weight Q over 2 is in every case the measure of the work performed, which is always the same in the same configuration of the system and is independent of the path of transference. A contrivance which would develop by means of a constant weight a force varying with the displacement would be, for example, a wheel and axle, figure 56, with a non-circular wheel. It would not repay the trouble, however, to enter into the details of the reasoning indicated in this case, since we perceive at a glance its feasibility. If we know the relation that subsists between the work done and the so-called vis viva of a system, a relation established in dynamics, we arrive easily at the principle communicated by Courtevron in 1749 to the Paris Academy, which is this: for the configuration of stable equilibrium at which the work done is a maximum, the vis viva of the system in motion is also a maximum in its transit through these configurations. For the configuration of unstable equilibrium at which the work done is a minimum, the vis viva of the system in motion is also a minimum in its transit through these configurations. A heavy, homogeneous triaxial ellipsoid resting on a horizontal plane is admirably adapted to illustrate the various classes of equilibrium. When the ellipsoid rests on the extremity of its smallest axis, it is in stable equilibrium, for any displacement it may suffer elevates its center of gravity. If it rests on its longest axis, it is in unstable equilibrium. If the ellipsoids stand on its mean axis, its equilibrium is mixed. A homogeneous sphere or a homogeneous right cylinder on a horizontal plane illustrates the case of indifferent equilibrium. In figure 57, we have represented the paths of the center of gravity of a cube rolling on a horizontal plane about one of its edges. The position A of the center of gravity is the position of stable equilibrium, the position B, the position of unstable equilibrium. We will now consider an example which at first sight appears very complicated, but is elucidated at once by the principle of virtual displacements. John and James Bernoulli, on the occasion of a conversation on mathematical topics during a walk in Basel, lighted on the question of what form a chain would take that was freely suspended and fastened at both ends. They soon and easily agreed in the view that the chain would assume that form of equilibrium at which its center of gravity lay in the lowest possible position. As a matter of fact, We really do perceive that equilibrium subsists when all the links of the chain have sunk as low as possible, when none can sink lower without raising in consequence of the connections of the system an equivalent mass equally high or higher. When the center of gravity has sunk as low as it possibly can sink, when all has happened that can happen, stable equilibrium exists. The physical part of the problem is disposed of by this consideration. The determination of the curve that has the lowest center of gravity for a given length between the 2 points A, B is simply a mathematical problem. Collecting all that has been presented, we see that there is contained in the principle of virtual displacements simply the recognition of a fact that was instinctively familiar to us long previously, only that we had not apprehended it so precisely and clearly. This fact consists in the circumstance that heavy bodies never displace themselves, move only downwards. If several such bodies be joined together so that they can only find displacement independently of each other, they will then move only in the event that some heavy mass in the whole able to descend, or as the principle expresses it, only in the event that work can be performed. If, extending the notion of force, we transfer the principle to forces other than those due to gravity, the recognition is again contained therein of the fact that the natural occurrences in question take place of themselves only in a definite sense and not in the opposite sense. Just as heavy bodies descend downwards, so differences of temperature and electrical potential cannot increase of their own accord, but only diminish, and so on. If occurrences of this kind be so connected that they can take place only in the contrary sense, the principle then establishes, more precisely than our instinctive apprehension could do this, the factor work as determinative and decisive of the direction of the occurrences. The equilibrium equation of the principle may be reduced in every case to the trivial statement that when nothing can happen, nothing does happen. It is important to obtain clearly the perception that we have to deal, in the case of all principles, merely with the ascertainment and establishment of a fact. If we neglect this, we shall always be sensible of some deficiency, and will seek a verification of the principle that is not to be found. Jacobi states in his lectures on dynamics that Gauss once remarked that Lagrange's equations of motion had not been proved, but only historically enunciated. And this view really appears to us to be the correct one in regard to the principle of virtual displacements. The assertion of the early inquirers who lay the foundation of a new department of investigation is entirely different in form and aspect to what follows. It is the business of the successors of those who have made the early researches more exactly to establish what the first teaches. More brains are required for this than is generally supposed. When the most important facts are once furnished, we are then placed in a position to work them out deductively and logically by the methods of mathematical physics. We can then organize the department of inquiry in question and show that in the acceptance of some one fact, a whole series of others is included which were not to be immediately discerned in the first. The one task is as important as the other. We should not, however, confound the one with the other. We cannot prove by mathematics that nature must be exactly what it is, but we can prove that one set of observed properties determines conjointly another set which are not directly manifest. Let it be remarked in conclusion that the principle of virtual displacements, like every general principle, brings with it, by the insight which it furnishes, disillusionment as well as elucidation. It brings with it disillusionment to the extent that we recognize in it facts which were long before known and even instinctively perceived, our present recognition being simply more distinct and more definite, and elucidation in that it enables us to see everywhere throughout the most complicated relations the same simple facts.